Hello, my name is Irene Abril Cabezas. I'm a PhD student at the University of Cambridge, working with Blake Sherwin. As part of my PhD, I'm part of the Atacama Cosmology Telescope and the Simons Observatory collaboration, and I work in the ACT lensing group. Today, I will be talking to you about this very new, exciting CMB data set. This is doing cosmology. We're very close to completing the first cosmological analysis using data taken during the day. That is, how does this work? It doesn't work. That's fine. It's not working. I have to click on the screen. Try again. This is screen? Okay, anyways, this is data taken during the day. So why this is exciting and why should you care? So as we heard from Satya, really the future of CMB from the Chile is very bright. We have funding for the next 10 years, at least with Simons. The Atacama Cosmology Telescope just finished, and this is a great site. This is a picture of the site on the map. It's our site is located in Cerro Toco in the Atacama Desert in Chile. It's a great place to do cosmology. Hola, Anna, it's working again.
Works. Give me this one and I will charge you. Sorry about that.
No, that's okay. Hello. We're located at 5,200 meters in altitude, and this gives us a very low water vapor content, 1.2 millimeters, which you might think is low, but it's actually 3 times higher than in the South Pole. But we have that the South Pole doesn't, is access to 70% of the sky. What also happens is that half the time that a telescope in Chile observes will be during the day. Okay, so if an analysis with nighttime data is challenging, with daytime data is even more. But we should do it. Why? Well, our forecasts say that with CMB lensing alone, Simons Observatory, nighttime plus daytime data, will be able to place a constraint on the neutrino mass sum of 30 millielectron volts, well below the 60 millielectron volts limit from neutrino oscillation experiments. This is a factor of 5 increase from one of the current state-of-the-art measurements with ACT that I'm showing with the gray data points there. And so really to make this work, we need to make daytime work. And this is what I'm showing here is like a Pathfinder, hello, is somewhere there. It's a Pathfinder analysis with the Atacama Cosmology Telescope to really show you that we're gonna be able to do this with ESO, and it's gonna be amazing. Okay, so the Atacama data, the Atacama Cosmology Telescope really probed the small angular scales and the polarization component of the CMB with unprecedented sensitivity. So the ACT final data they released, DR6, is really a great data set to do cosmology, and in particular to measure CMB lensing. What is CMB lensing, you may ask? Okay. Hola. Hello. On the way to the telescopes, the CMB photons are deflected by intervening large-scale structure, and this phenomenon is known as weak gravitational lensing of the CMB, or CMB lensing for short. Lensing changes the statistics of the CMB, correlating formally independent modes. So those are two temperature fields, different L, so they don't talk to each other because the CMB is a Gaussian field, but now this quantity is proportional to phi. What is phi? Phi is the projected matter density field along the line of sight. So with a measurement of phi, you can measure anything that affects the matter power spectrum, such as neutrinos. So how do we do this? We use quadratic estimators, which essentially take two CMB maps to uncover the correlation between them induced by lensing. We're here with this integral, we're summing over all possible modes. And this is what Frank Chu, which was in Cambridge, now at Stanford, used to reconstruct with the ACT lensing group. The projected matter density field over 20% of the sky, and you can see by eye dark matter dominated structures on few degree scales. So this is really great and looks pretty. Let's measure it quantitatively. For this, we take the lensing power spectrum, which tells you how much lensing there is as a function of the angular extent of the lens. And in red is the data points that Frank measured, and in black is the lambda CDM prediction of a Planck-like cosmology, and it shows perfect agreement between the two, which is really exciting. And this year we went one step further, and we combined ACT, Planck, and SPT lensing band powers all together. Well, we didn't combine them. First, we checked that they both gave consistent amplitudes of structure growth. And then we combine them, and we obtain a 1.1% measurement on sigma 8 when we combine with BAO. So this really tells us that lambda CDM predictions really work on a broad range of scales and redshifts. And this sigma 8 measurement is the most precise measurement of this parameter from a galaxy or CMB lensing to date. Of course, as I was saying, we can probe neutrino masses too, because neutrinos, when they become relativistic, non-relativistic, sorry. When neutrinos, when they become non-relativistic, they suppress the matter power spectrum at the few percent level. So because we, with lensing, we probe the matter density field, we can also measure this. But we find the same puzzling results as other groups and experiments have found. We also freed tau, and yeah, things happen. But let's do better. This is the signal that we want to measure, and that's our current noise. We can do better. How are we gonna do better? We're gonna add daytime data, and it's gonna be amazing. This is working. This is working. Let me introduce you the data set. So the TELES-ACT ran during the day 2, and we took data from 2017 to 2019. We mapped 8% of the sky with a mean depth of 8 microkelvin arc minute. And then in 2020, from 2022, we changed the scanning strategy, and we instead map half the sky basically with a mean depth of 27 microkelvin arc minute. Now, what's the problem with this data? It is challenging. Why? Because the sun is there, it hits the telescope mirror, and this causes pointing offsets and beam deformations, also known as it's really difficult to characterize the telescope. But after appropriate sky cuts, we're sure that we can make this data set reliable for lensing with appropriate scaling to the nighttime data. And we've checked that this works now with more than 100 map level and band power level null tests that tell us that this is really working, and this measurement is going to be, it's possible now with ACT, and it's going to definitely be possible with SO. Here I'm showing an example of a map level null test, and here's an example of a band power level null test. Basically, you just, for map level, you just subtract 2 data sets, 9 day versus night, and if you've done everything well, there should be nothing there that is not lensing, and in fact, there's nothing there. And also when we reconstruct the band powers, that they are also consistent with each other. And so we're achieving a signal to noise of 30 from daytime only data, which is like super exciting. Can we do even better? Yes. Why? We can, for example, improve the sky cuts. Can we go to wider sky areas? And as soon as I tell you go to higher sky areas, you should be like, no. Why? Because galactic foregrounds are non-Gaussian, and this might mimic the non-Gaussian signature that quadratic estimators are designed to measure. So of course, we know this, and that's why we've kept our masks and lots of null tests checking that we don't have any galactic foregrounds on our data set. But if we want to go wider, what we did here in this work, we run our lensing pipeline through a whole suite of galactic foreground models, and we found that this is indeed, and then we check how much our lensing power spectrum would be biased, and we've checked that for ACT. This is not the case. We're good. Everything's fine. But for SO, it might be a problem, which is great news for us, or for me in particular, because it means that I can continue working on this. We can do data, we can do improved sky cuts, and it's going to be amazing. And so with this, I finished. I've presented to you the first Pathfinder analysis with CMB lensing with daytime data, and it's really going to be great with the Simons Observatory. Our signal to noise, it's going to reach levels we haven't reached before, and we will also be doing further improvements used in mitigation strategies from galactic programs. And of course, our closing remark were the neutrinos. Hopefully we can answer this with CMB lensing. Thank you.
Well, Irene, very exciting questions and several, but
Sorry, I'm a theorist. So
Yes,
I love
like-
to ask, but don't you get a lot of light radiation from the sun?
I mean, we obviously avoid the sun. Like, we don't point at the sun and say, like, CMB, let me know. No. So, okay. So, we don't point at the sun, and then we check for sight. So even if you're not pointing at the sun, you might get some sight of thing. We also make those sort of cuts, and then what we're left is some like diffuse background that you can basically just like it's just kicking at low angular scales that we're not using anyways. So so we do small angular. This is kicking at small angular scales, and of course we also we exclude side up leakage when the beam looks weird. So yeah. When I started the project, I was like, this is not possible, is it? But yeah. What allows you to distinguish? Right. So at the TOD level, so when we at the TOD level, so when we gather the data by the telescope, we already making the cuts like beam quality, like the point source should look like a point source. If it looks like a drawing of a child that like just very weakly, that data doesn't go into the map making. So they're like beam cuts. We exclude the sun already, and then we have this clean data set, and then we compare this to night, and then we see that this actually we can compute some transfer function that takes you from data, this transfer function, and it gets you to night. And this is, and then we check that this procedure works with all the null tests that check for this sort of systematics.
can I ask another question? Okay, so maybe I can ask you. You said multiple times that you can do lensing, but what about primary?
Yeah. So
I would imagine that it's like
right. I guess the key here is that the signal to noise that we're measuring is around 30, and for primary, it's like, I don't know what the signal to noise of primary, 1,000. Like, it's an order of magnitude. Like with primary,
then it has to be easier to do, right? If the signal is already so high that maybe it's easier to do primary first, and then lensing will come also almost automatically out.
So I guess so the estimates that we have to transform to make daytime reliable have error bars, and these error bars, these error bars are like low enough that you can do a signal to noise measurement of 60, but this wouldn't allow you to do any more. Like you cannot do precision cosmology on the 2-point function because of these estimates are still approximate. They're good enough, but not like 2-point function. Yeah.
The other question is about this transfer function mentioned at also not yet. So you have to correct, so assuming that the night is correct, but then this is an L-dependent correction.
Yeah. Yes.
But this is some fiducial model, right? I'm confused. It's not obviously that you can do then like neutrinos if you have some L-dependent transfer function.
It's a fiducial. I mean, it only comes if you just do in comparison to night, and that there is no model there. You just take as BAM powers. Yeah.
The CMB level, right?
Yes.
T and T, just T, okay. Okay, let's thank you then again.
So, hello everyone, I'm Marina Cagliari, I'm a postdoc at LabTH in Annecy, France, and today I'm going to talk about a few works I've done